Okay, so this is a report on multiple linear regression on parameter data. The parameter data comes from stat2 data state package on R. There are altogether 7 variables in that data set. It looks like this. 7 variables, and the dependent variable y is calculated in terms of kilocalories, which is the number of calories burned. Among these 7 data, 2 of them are categorical data. The variable rain is read in terms of cloudy day, rainy day, or sunny day. The variable day type is read in terms of either weekday or weekend. Now, the goal of this research project. There are 2 main questions that we'll look forward to find the answer to in this project. The first one is going to be, does a multiple linear regression model correctly fit on this data? The second one, if it does, what are the variables that have significant impact on that, the most significant impact on that model? Let's see. Okay. This is a generic skeleton of how the study was conducted. First, we analyzed the data set for visible outliers or missing data, and then we generate various models. We go from the largest possible model to refining them to a model with only the most significant variables. How we do that? We look at the ANOVA table of different models, compare them, pick the best one out of them. Then we do a stepwise reduction. Then we check for multicollinearity. We keep removing variables every time. And then finally, once we have our best picked model, we do some analysis on that, like maybe hypothesis testing or something like that. Let's see. Okay, the data set. First thing we look for is missing value. Fortunately, this data has already been treated for missing values. You can see, if you calculate the sum of all missing values, it says 0, so there's no missing value. Now, and then, okay, so I've already been through this. 2 of them are categorical data. Then we try to look for any visible outliers, any like very noticeable outliers. So we plot each variable against the dependent variable. See, and when we see that, we don't have any data or x variable that has a significant outlier that could possibly impact our data set. See, this one is for the rain, which is calculated either cold, rain, or shine, 3 category variables. If you look at the day type, it's going to be the weekend or weekday. So, the first task is to assign indicator variables on the categorical data. How we do that? Here. Now, 2 types of day type is going to yield 1 x variable. 3 types of rainy day or cold day or sunny day are going to yield 2 x variables. Now, there's going to be 6 combinations of different types of model here. 6 possible combinations of indicator variable that will set the, for example, when there is weekday, our so let's look at this combination of weekday and then C, cold. Weekday and then C, cold. It means all our x5, x6, and x7 are going to be assigned 0. So we're only going to have x's from 1 to 4. And likewise, either 1s or 0s or 1s or 0s, depending on the combination. Maybe weekend and C, weekend and R. So we're going to have 6 different combinations for this one. Now the next thing I did was, after I assigned the indicator variable, what I did was I looked for obvious kind of interaction. Like there can be multiple interactions among the variables, but I looked at the obvious ones. I took one big model without interaction, and then one big model with possible obvious interaction. And just looked at the model on R, like it's all the t-values, the sum square values, and all for both models. Next thing. Next step, I compared those 2 models to see which one I could pick. If you compare using the ANOVA table, we realize that model 1 was better suited for this data compared to model 2. So the model without interaction was better suited compared to the model with interaction, with an obvious interaction. Now, so for now, this is the model we pick. The one without interaction, the largest model of all variables without interaction. Now we try to keep removing the unnecessary or less significant or variables with multicollinearity. The first thing we do is a stepwise regression. This is a both-sided stepwise regression, both forward and backward. You can see, this is a snapshot of my R code. You can see that finally, out of all 6 regressors, we only get 1, 2, 3, 4, 5. So one of them, which one, day type, no, 2 of them is removed. You can see here. This one, both is for rain. Out of 6 regressors, 2 of them are removed after stepwise regression. We only have 4 of them. So the rain, minimum, steps, and moderate. 2 of them are gone. So at this moment, our model looks like this, currently. Now what do? We check for multicollinearity. Now there is a VIF function on R. VIF stands for variance inflation factors. That goes through every regressor and calculates the ZVIF value for every regression. Now how this works is, the larger the ZVIF value for any regressor is compared to, or however, the more the ZVIF value of a regressor is far away from the value 1, there are more chances that it's gonna have multicollinearity. For example, look at this. So these 4 were our current regressors that we picked. If you look at the GVIF value, comparatively, out of all 4, these 2 are significantly far away from the value 1. Or you can also look at the inverse form. You can look any one of them. This is a simplified form. This is actually GVIF form. So even here, these 2 are significantly away from the value 1 compared to these 2. So we see an obvious multicollinearity here. This one is also debatable, but comparatively, these two obviously are more likely to have multicollinearity. So what do? We remove these 2 from our model. So what does our model look like now? This is what our model looks like. What variable did we pick finally? We pick steps and rain. Remember, in rain, the rain consists of 2 x's from our combination. So this is what our model looks like. Finally, if you look at the adjusted R square, it's 0.91.9199, so it's pretty much good at this moment. Now, let's look at this model. This is the residual plot, fairly funnel-like or tunnel-like, whatever you like to call. And one thing I realized from my, I went through a few online papers on regression analysis. One thing what I realized was not only it has to be a funnel shape, but the distribution has to be random. There should not be any vivid shape. For example, maybe U shape or straight line. Look at this. This one does not have a shape. It's not a parabola, it's not a line. There's no vivid shape. It's pretty much random. So what can we infer from here? A random funnel-like would suggest that this is fairly linear now. Now what does that imply? Since this is fairly linear, we don't have to apply any transformation. See where this goes? The regression, the linear regression is a good thing to do on this data. It shows a linearity. Okay, there was supposed to be, okay, here. Now this is the normal QQ plot, pretty much good, mostly linear on the largest chunk. So this suggests that this would have, the errors would have pretty much normal distribution, fair enough, and with constant variance, looking at both plots. Okay, so these are the inferences. So the first one, it is randomly distributed, so the relationship is linear, and then it is tunnel-like compared with the horizontal line, it is evenly spread both upwards and downwards. So it has a constant variance. Looking at the QQ plot, we know that it is fairly normal. The largest chunk was in the straight line, and then there is an unknown but a constant variance that we can verify. We don't know the variance, but still it is constant. And they are independent. Okay. Now the analysis. So again, this is what our model looks right now after everything. The first thing I checked was for the significance of regression. The null hypothesis is all the betas are 0. Alternative hypothesis is at least one of them is not 0. So we've done this in class before. There are two ways we could do this with. The first is look at the p-value, compare it with alpha, or look at the f-naught, compare it with the tabular f-value. In both cases, in the first case, the p-value is significantly less than alpha. In the second case, the f-naught is greater than the tabular f-value. So f-naught is rejected, which is an obvious result. We know that. We're just verifying with the significance test. Again, I try to check. See, again, here at this point, we only have two regressors: steps and then rain. I try to check for the obvious one because see, the regressor steps compared to the number of calories. The more steps we take, the more number of calories we're gonna burn. That's the obvious regressor. So I try to check the significance of that regressor. Again, pretty obvious result. This is my reduced model, only keeping the rain. By the way, here, this is the reduced model. Removing the rain. Removing the steps, only keeping the rain. Remember, we also had x3, which was for step, but this is the reduced model, when beta 3 is equal to 0. So this is the reduced model, and if you find the f-naught value, it's going to be greater than the tabular f value. Again, the null hypothesis is rejected, so steps has significant effect on the model. That's our outcome. Before conclusion, a few limitations. For example, I was wondering if there was a column for maybe the average temperature of the day, because see, if we take same amount of steps, or if we walk the same distance on a sunny day or comparatively hotter day, then we're gonna burn more calories, right? Compared to the colder day or something like that. So I think if there was a column for like average temperature per day, it would give better result. Also, this data only considers walking at a moderate step. Maybe if there was a column for like maybe running. So if we run the same distance as compared to walk the same distance, then we're gonna burn more calories. So that would have possibly brought better results. So those were a few limitations in the data. So the conclusion basically is, out of all the regressors, steps and rain are the most significant ones. And the obvious conclusion, the multiple regression model fits really good on this data. That's the main conclusion. And that is proven by the adjusted R squared. It's a pretty decent number, 9199. That's it.